this lecture we're going to do chapter 3, and this unit is all about vectors. And so let's take a look. You've already learned a lot about vectors last year, and you've learned a lot about vectors in pre-calculus as well, I think. And so I think this is going to mostly be a review. We're going to be talking about how we're going to use these things in physics and kind of getting our notation right and get some extra practice here. So a vector. Vector is a quantity with both magnitude and direction, and so when we're using vectors, we have to use vector math. A scalar is a quantity with magnitude only, and there we can use ordinary arithmetic math. Properties of vectors, okay? A vector slid parallel to itself is not changed, so you can take the vector and move it anywhere around. As long as it's pointing in the same direction and has the same magnitude, it's still the same vector. If a vector is shown as an arrow, so typically the convention is the length of the arrow indicates the magnitude, and the direction obviously indicates the direction. Okay, you can add vectors only if they have the same unit, and you can add the magnitudes only if they're in the same direction. Okay, when you're multiplying a vector by a scalar, the units multiply, the numbers multiply the magnitudes, but the direction does not change. All right. So what's next? When you're adding them, graphical methods, right? You add head to tail. That's when you're adding two or more vectors. If you're adding two vectors, then you can use the parallelogram method. And a vector sum is called the resultant. And so there are a couple of examples here. The head to tail method, where you've got A, B, C, R is the resultant, and the parallelogram method, just A and B, where you sort of double the vectors and make a parallelogram out of it. Vector subtraction, really simply, A minus B, okay, is the same thing, I like to think of it this way, as A plus negative B. So what's the negative of some vector? What you do is you flip it. You flip directions. That's it, when you take the negative of a vector. So if this is A, and it looks like this is B, if I'm doing this, then I'm doing A, try to reproduce that there, plus negative B. So B goes this way, so kind of like that. So this is the resultant. All right. A plus negative B. That's it. And so we can do arithmetic with this as long as we keep in mind our rules about vectors and vector arithmetic. Vector components, any vector we can split into horizontal and vertical components. You did that a lot last year, especially with things like projectile motion, motion in 2 dimensions. That's what we're getting into here, motion in 2 dimensions and that sort of thing. X component, Y component, right? The X component is A cosine theta, as long as you set X as the horizontal, right? Y as A sine theta, as long as you're measuring the angle from the horizontal, the positive x-axis. If you're measuring the angle from some other axis, this changes. So you got to be careful about where the angle is. Magnitude is expressed. So yeah, we're filling this in here on this chart kind of thing. So this is AX is A cosine theta. AY is A sine theta. The magnitude can be expressed like this. Or sometimes you might just see it written as this. If it's written like that without the vector line above it, then we mean the magnitude most of the time. And the direction, theta, we can find theta if we do inverse tangent of AY over AX, the vertical over the horizontal. Some basic trigonometry there. A lot of times rectangular components are the most useful. That's probably what we use most, but we won't use that all the time. There are also rotational components. There are all kinds of ways to break something up. There are different coordinate systems. There's spherical, cylindrical coordinate systems. Not that we're going to look at all those this year, but just to be aware. Again, the vector addition. Another way of doing vector addition is by adding the components, right? So if I wanted to do A plus B, I could find AX, AY, right? bx, by. I can add the individual components and then put the whole thing together again. There are times where that's going to be helpful as well. You see some examples, some of these more challenging examples. Okay, the unit vector. Unit means 1, right? And it's a vector. So all the unit vectors are vectors that have magnitude 1 and they point in some direction. These are useful because if you multiply something by 1, the magnitude of that thing doesn't change. If you multiply something by a unit vector, the magnitude doesn't change, but you're giving it a direction. All right, so here's how you can think about this, right? Unit vector, magnitude of 1. Useful unit vectors are those which point in the x, y, and z direction. X is I, y is j, and z is k, right? So the I, j, k, which you've seen, I think, at least in pre-calculus. We're also going to have other vectors that point in the radial direction for things that are circular, spherical, oftentimes. So expressing vectors in unit vector notation is easy if you understand vector components. If you don't understand vector components, breaking things up into their vertical and horizontal components, then this is going to be challenging. Magnitude can be given by this, the x component squared plus the y component squared plus the z component squared. This is the three-dimensional Pythagorean theorem. And so you can find the magnitude this way. Just take these components of the vector, square them, add them, take the square root, and you get that thing. Okay, so here's an example 1. Find the magnitude and direction of this two-dimensional vector. Why is it two-dimensional? There are 3 dimensions written here because the z dimension is 0. Right, 0k, meaning we have 0, nothing in that dimension. So let's take a quick look at this. So if a is negative 5I minus 12j plus 0k meters, then the magnitude of a is the square root of 5 squared plus 12 squared. So that's 13 meters. And inverse tangent of the vertical over the horizontal is 12 over 5. And I'm going to add 180 to that, and we'll see why in just a second. Okay. So here's the vector in unit vector notation. Notice what we wrote. This is I, j, k. Sometimes I'll call this I hat, j hat, and k hat because they each look like they're wearing a hat. And we found the magnitude, and we found the direction. Notice I had to add 180 degrees. If you put this into your calculator, 12 over 5, even negative 12 over negative 5, you're not going to get this number. It's because calculators are stupid, and you're not. Okay? Don't rely so heavily on calculators. You've got to use your common sense as well. So why did I add 180 degrees? Well, if I look at this vector, this is negative and negative, so this is over here somewhere, right? Negative 5. So it's going to be something like this. Right. So when I do inverse tangent of this positive thing, that's going to give me some angle here. Right. That'll give me this angle. So I have to add 180 degrees to get it into the right quadrant. That's one way that you can think about this. Right. Or you could do, yeah. So be careful when you're using these angles, which quadrant you're ending up in, because the calculator won't necessarily do that for you. Okay, so now we're going to find a unit vector notation for something that's given to us in terms of magnitude and direction. First thing we should do is draw this, and this looks like this. This is 20 degrees that way. Right, so that means that from the x-axis, from the positive x-axis, this is 110 degrees. Right, let me do 2 lines there to differentiate between the two of those. And this has a magnitude of 25 meters per second. So if I do 25 cosine of 110, now I can use this angle, and 25 sine of 110, that's going to give me this. A is negative 8.6I. Now that's good. I'm in the negative I direction. So I'm expecting to get a negative I there, but I'm saying to get positive j. And is that what I get here when I do 25 sine of 110? Yes, I get plus 23.5 j meters per second. Right? Don't forget the units at the end. Units are important. All right, so here's another example from the text now. So we're told that C is 3i plus 4j. So let's draw this out. This is C. And we're told that B is added to C, and the resulting vector is in the positive direction of the y-axis. Okay. So let's say that this is the resulting vector. That means that B has got to be something like this, right? So I'm thinking through, I'm drawing here what is what's happening. And so if this is C, and I want something that results just like this, then B can be that. Notice it says, with a magnitude equal to that of C, right? The resulting vector. So actually, it won't be this. What's the magnitude of C? It's 5, right? So this has got to go up one more. See, I got that wrong. Read carefully. So R is like this. That means B has to be like this. Now, in unit vector notation, this is simple. I need B to go up 1 and to the left 3, right? And so then B is negative 3j plus k. I could put 1k there, but it's redundant. And so then the magnitude of this is going to be the square root of 3 squared plus 1 squared, which is the square root of 4. 9, so square root of 10. And the square root of 10 is 3 point something. The important thing is getting at least that far, right? So let's go on to the next packet. What is my next packet, but for you is probably one whole packet. No, this is easy to show two-dimensionally, right? Here's x, here's y. But what if we have vectors going into the page or out of the page, right? I want to show some vector where the vector is coming out towards you or going in. When we think about these vectors, think of an arrow. An arrow has feathers on the back, and it's got a point in the front. Right? If an arrow was coming at you, you would see a point. Right? That would be the primary thing. And so we draw this. This means that a vector is coming out of the page. And then if you're looking at the back of an arrow, a vector that's going into the page, you would see the feathers. And so this, it kind of looks like the cross of the feathers, right? This means going into the page. So we will use this. This is a convention that you can use even on the AP test or anything like that. So this means out of the page, this means into the page. All right, and now we're going to talk about the scalar product. Scalar product or dot product, which I think you've studied before. But again, just a little bit of review. One example of a scalar product is work, right? And so work is a scalar. So see that the W is there, is a scalar, right? F d cosine theta. So here we're talking about the magnitude of F. This is the magnitude of the displacement. And this is the angle between them. Because F and D are both vectors, right? Not here, these are the magnitudes that we wrote, but F in itself and D in itself is a vector. And so there's some angle between them, and that's what is going here. Of course, you should know that. And so the first definition of a scalar product, so A dot B is AB cosine of theta. And these are the magnitudes of A and B. So we could do this just to make that clear. It's A and B. Although we can write it without the vector notation and understand that it's still just the magnitude of those things. Okay, and so what is A? This is vector A. This is vector B. This is the magnitude of A, right? The magnitude of B. And this is the angle between them. Again, I hope that that is mostly a review for you. So let's talk about some of the what ifs, right? What if two vectors are parallel? Well, if two vectors are parallel, that means they're in the same direction. Since if they're in the same direction, then theta is 0. And what's cosine of 0? 1. So, the answer to that question 1 there is then A dot B is simply equal to A times B, the product of their magnitudes. 2. What if they are anti-parallel? Well, if they're anti-parallel, that means they're like this. Right, one's in one direction, one's the other. The angle between these is 180 degrees. What's cosine of 180 degrees? -1. So in that case, if they are anti-parallel, then it's negative the product of the magnitudes. And then what if the vectors are perpendicular? If they're perpendicular, that this is 90 degrees, and if this is 90 degrees, then cosine of 90 is 0. And so in that case, if they're perpendicular to each other, their dot product is 0. Okay. What if the vectors are equal? Well, if the vectors are equal, so now we're on to number 4, then A dot B would be like A squared, if they happen to be in the same direction. All right. And one example of this is if I take the unit vectors, like I dotted with I. Well, I dotted with I, these are parallel, so it's going to be this, but the value of these, the magnitudes, are 1. So I dot I is 1. Keep that in mind, we're going to use that in a derivation in a minute. J dot J is 1, and K dot K is 1. Okay, so how are we going to use that? So talking about the scalar product. And then 5, when is the dot product equal to 0? When they're perpendicular, which we said here, or if one of the vectors is 0. Now let's take a look at definition 2 of the dot product. So definition 2 is this. A dot B, and now we need the unit vector notation, is AXI plus AYJ. Here we mean the x component of A, the y component of A, plus the z component of A, times the x component of B, plus the y component of B in the j direction, plus the z component of B in the k direction. This is my alternate definition of dot product. Okay, so what does this look like then when I distribute this whole thing? Because now I'm going to take this times this, this times this, this times this, this times this, right? The whole thing here. So this equals, this is going to take a while. Now that took a little while to write out. Don't worry, you're not going to have to do this every time, because watch what happens now. I'm going to go through and cross out everything that's 0. Remember we said that the dot product of, well, there should be dots between each of these. Dot, 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 dot. The dot product of any perpendicular vectors is 0. And so these two are perpendicular, right? I and j, I and k perpendicular, j and k perpendicular, j and I perpendicular. These are perpendicular, these are perpendicular. And so I'm just left with these. All right. What does this mean then? This means that the dot product, when I'm using unit vector notation, is simply equal to, and these, by the way, what are I? I dot I is just 1. And so we can simplify this whole thing to just be the product of the x components plus the product of the y components plus the product of the z components. That's it. So this is our second definition for the dot product. You should have something like this in your packet. So now we've got two definitions of dot product here. And since we have two definitions, we got this and AB cosine of theta. Now notice that I have another way of finding the angle. If I have some three-dimensional vector expressed in unit vector notation, and I can find the magnitudes by using the three-dimensional Pythagorean theorem, then I can actually find the angle. The angle between two vectors that are in three-dimensional space. It can be confusing according to the formula here, where I just take cosine of theta is equal to this divided by this. And then you can use inverse cosine to find that angle. Okay, so here's some example one, some visual problems. Part A, what is the, so we're saying what the dot product of these. Well, in part A, 1A, that's 0 because they're perpendicular to each other. In B, it's negative 120 because A has magnitude 10, B has magnitude 12. They're anti-parallel, so negative 120. In C, they've got a 60-degree angle between them, and cosine of 60 is 1/2. And so it's 120, half of that, 60. And D would be 0, right? B, what direction is B going? B is into the page, right? Because we see the feathers of the arrow, the back of the arrow. And that's perpendicular with A, so that's 0. Where am I going? Okay. So let's take a look at example 2. In example 2, I've got two-dimensional vectors, but they're two-dimensional and they're in different planes. One is in the xy plane, the other is in the xz plane. And so we need to find A, the magnitude of each vector, B, the dot product, A dot B, and then C, the angle between the vectors without using the law of cosines. All right, so for part A, to find the magnitude of A, I'm going to do the three-dimensional Pythagorean theorem, although you could just do it two-dimensionally. And you get the square root of 13. The magnitude of B is square root of negative 1 squared plus 2 squared, so we get the square root of 5. All right, so there's the magnitude of each one. The dot product B, we can find the dot product by multiplying the components, right? So 2 times negative 1 plus 3 times 0 plus 0 times 2, and so I end up with negative 2. That's it. And notice, again, this is a scalar. It's a scalar. It gives us a scalar at the end. I don't have any direction at the end of a dot product. Okay, and then see the angle between these two vectors. Not those two, but the ones that are described here. And so I know that, right, A dot B over the product of the magnitudes will give me cosine of theta. Well, the product of the dot product is negative 2. The product of the magnitudes would be square root 13 over square root 5. So if I do the inverse cosine of this thing, so negative 2 over A dot B, so root 13 times root 5, then that will give me 104 degrees. So now in example 3, we're given this three-dimensional vector, and we want to know the angle between vector A and each of the three axes. So what are we doing here? We know the way to find the angle is to do this inverse cosine thing, right? So inverse cosine of, and then we put in the dot product over the product of the magnitudes. I don't know why I did BA instead of AB. That'll give me theta. So what do I need to do? I need to do this with each of the axes. And what's the axis? Like, how do I find well, if I take the x-axis as just being the vector I, right, that gives me the right direction, and it doesn't have to have any particular magnitude. As a matter of fact, having magnitude 1 is going to be the easiest thing. So all you need to do is do the dot product with this vector and some vector along the axis. Doing it with 1 is going to be the easiest thing. Why? Because if I take this vector A and I find the magnitude, 2 squared plus 3 squared plus 6 squared, square root, gives me 7. Right? But notice that for I, the magnitude is 1. For j hat, the magnitude is 1. And for k hat, the magnitude is 1. So when I'm doing this, it's going to be a lot easier, right? So for the x-axis, I do inverse cosine of a dot b. So when I do a dot b, what am I doing? I'm taking the dot product of a with the I unit vector. And so this ends up just being 2 because, if a is 2i plus 3j plus 6k, I is just 1i. And so this, the dot product of this and this is just going to be this times this. So I just get 2 over the product of their magnitude, so it's going to be over 7. And so this is going to end up being 73 degrees. By the way, do I expect any of these to be more than 90 degrees? No. I'm expecting all of these to be less than 90 degrees. For the y-axis, again, cosine, inverse cosine of, and now the j vector is 1j. That's what that means, right? So 1 times 3 gives me 3 as the dot product, and the product of their magnitudes is 7. So this is going to give me 65 degrees. And then the z-axis will be inverse cosine of, the dot product would be 6 times 1k, right? So 6 over 7, and it gives me 31 degrees. So that's it. Example 4, some more kind of visuals. A and B, letter E, A and B are perpendicular, so the dot product is 0. F, again, perpendicular. A is coming out of the page, that's the arrow point coming towards you, 0. G, here it's 120 times root 2 over 2, ends up being 60 root 2. And in H, these are anti-parallel, right? A is going into the paper, B is coming out of the paper, 10 and 12, so negative 120. For example 5, now you're given, again, 2 vectors, and it says, given the following vectors, find the angle between them using the scalar product. Okay, and then it says, find the component of A that's in the direction of B. Okay, and so what we're going to do here, I would say try A using the same kind of method that we used for example 2, except now this is in all 3 dimensions. Oh no, it's not. This is still in still 2-dimensional things. And I'll put it up here on the board. Okay, so the answer to part A is 70 degrees. This is the dot product. These are the magnitudes. So inverse cosine of the dot product over the product of the magnitudes gives me 70 degrees. Now I want to find the component of A that's in the direction of B. In other words, if this is A and this is B, I want to know if I were to project A onto B, right, like a perpendicular projection, how much of A is in the direction of B? And this is what we mean by components. We're not always going to be splitting up into X, Y, and Z components. Here I'm finding the component of A that's in the direction of B. And so the way I do that, right, what is this? Well, this is just cosine. If this is theta, then this is A cosine of theta. So I take the magnitude of A, which is root 13, and I multiply it by cosine of 70, and I get 1.23, and that's it. We don't have any units in this case. So that's chapter 3.